Just some people do, and they're like, they close the browser down, and then I can't tell that they've even looked at the material itself. All right, let's get going here. Hey, I'm not handing out a sheet of paper today. That means everything that I tell you to take notes on will go in your book of truth. Okay. All right, back to the original question. Anyone have any issues with the homework? Not true. You asked me yesterday, and we did a couple together. Sharing is paused. Bring your shared window to the front. I thought I did. Stop share. Let's share again. Maybe that's the issue. I'm talking. Yes, I am talking to myself. If I answer myself, we got problems. Share. How about this? Do you like this better? Oh yes. All right, no questions. I mean, it's going to be pretty sweet. Usually I have my own student advisor. I don't get to walk around, but this year's different. So you guys get the bonus plan of seeing me frequently in your student advisement classroom. And Chandler, what are we not going to do in student advisement? What are we not going to do? Okay. Chandler. All right. We are going to do our homework. It's your perfect chance to get it done. You don't have to do your math homework. If you want to save that for home, that's fine. But you got to use your time wisely and do something. You know, the last 5-10 minutes, you'll never hear me complain, but we're not going to use 40 minutes to talk to our friends and neighbors about inconsequential things. We're going to get some work done. This school purposely makes your study hall student advisement your last period of the day. I mean, I literally, one of the years I went to high school, my study hall was third period. I mean, I was like, okay, great. I got all my homework for periods 1, 2, and 3. And then, you know, I had all this ton of homework that I would have at home. When, if it's towards the end of the day, it works so much better. Lunch, yeah, well, so, okay, I'm going to sidetrack here. So I grew up in Alabama. My high school did not have air conditioning. This is Alabama, south, as far south as you can go. There was no air conditioning except for the library. So I never ate lunch. I might be exaggerating slightly. There may have been 2 or 3 times, but I never ate lunch in high school. I would go to the library because it had air conditioning. And I was sitting there, and back then there were these things called magazines. I read magazines. And they had nice, soft, comfy sofa and these comfy armchairs and stuff. I would sit there and just read magazines for the 30-minute lunch, and then I would cool off and then go back to the hot sweat. We had these humongous fans. They would blow like a jet engine and stuff. I mean, literally, the teacher would be talking like this because the fan was so loud because it was so hot there. I don't know how we ever made it, but I do know that I live in Colorado. I'm never hot in Colorado. Yeah. Okay, there's literally no questions? Yes. 32. Let's take a look at 32. All right. I think I remember doing this with somebody yesterday. Was it you, Cadence? It was you? Okay. All right, 32 states the following. You get this shape, okay? You got a line. You got one ray that goes like this, and then you got a bisector. I'd put it dotted. It's not dotted. And then it's labeled 1, 2, 3. I'm not going to put any letters here. You're told that this is a bisector of this angle. If it's a bisector, you are not here for the class. Bisector. What do you think bisecting means? Take a guess. If I bisect a cake, guess what I just did? Thank you, but I'm not asking you. You cut it in half, right? So this dotted line cuts this angle in half. If I cut it, the angle in half, what can you say about angle 1 and angle 2? Are they the same or different? If you cut the cake in half, what can you say about the 2 pieces? Same or different? Unless you ask your brother or your sister to cut the cake, and then you know you just got shortchanged, right? But if a competent person cuts it in half, then 1 and 2 are exactly the same. So that's kind of the setup for 29 through 34. Further, we're told for 32, I'm going to leave out all this stuff. We're told that 1 is actually equal to x degrees. Cares. If 1 is equal to x degrees, and this is a bisector, how big is 2? The cake's cut in half. If 1 is equal to x degrees, how big is 2? So it's also x degrees. And lastly, you're told that this angle, is it 3x or 4x? Is 4x. Okay? So I'm going to erase that, and I'm going to put 4x degrees. Oh, that was horrible. There you go. That's the picture. The key to this, and you will see this many times this year, is this angle and this angle and this angle all put together make what angle? Who's this? Whose question was this? Was this you, Wes? Yeah. How many degrees in a straight line? 180. So this, using the angle addition postulate, this angle plus this angle plus this angle would equal, solve that equation for x and you're done. That idea of 2, 3, 5 angles put together that make a straight line equal 180, we will use at least 40 times this year, maybe even more. All right, anybody else? Okay, let's grade this really quickly. Quickly.
Okay.
All right, adjacent means next to. Now I'm going to give you 3 letters. Remember, the order could be different, just as long as the middle letter is the same. So the answer number 2 is angle ADL or EDT, right? We're skipping all the way through 8 because there's lots of answers. So we're going to pick it up with 10. 10 is acute. 12 is acute. 14 is obtuse. 16 is 1. That means the measure of angle 1. 18 is 180 degrees. I'll check your drawing. Picking up on 24. 24 is 1. 1. 1. Who had that question? Was it you, Micah? Somebody had the question, could you draw it this way? And I said, no, it's a straight line, so it goes through the line. One of you guys had that. 26, there's an A and a B. So A is 90, 90, 90. B, since it makes a straight line, therefore you've got 180 degrees. One of the angles is 87. What added to 87 is 180. That would be 93. And then the other one would be 87. Interior means on the inside, duh, right? Exterior means on the outside. So the answer to 28 is B must be in the interior of AOC, on the inside of AOC. 30 is 4, and 32 is 30. And 34, the last one, is 22. And that's it. That's all she wrote. All right, Seth, make sure they wind up in this basket. And then everybody else, get to your book of truth. And we're going to do a bunch of writing today. Not like paragraphs, but we're going to write a bunch of theorems and postulates. Bunches of theorems and postulates today. The nice thing is that, with few exceptions, not much of it is new. Couple things new, but not much. Hey, look at the board. If you ever see an A or B, and you can't remember what that means I'm taking section 1.5, the short day. I knew I was going to have to break it up into 2 days. So we'll start today. Yes, there will be homework. No. But we will finish up 1.5. So here's your homework. We're just doing 2 through 12. Right? And then we'll finish it on Monday. But you have to, by Monday, you have to have 2 through 12 done. We'll do, I don't know, 13 through whatever on Monday. Thank you. So our book of truth contains definitions, theorems, postulates, corollaries. That's all it's going to contain. We start proving things, which is today, we refer back to our book of truth, and the book of truth tells us how we can prove things. It's the justification. How do I know that Micah is 15 years old? What proof could we use? Birth certificate, passport, driver's license, something like that. That would be acceptable proof. For geometry, our acceptable proof is what's in your notebook. Okay? I will also say this. Occasionally, I might say something in class. If I prove it true, you can use it, but I don't think I ever say anything that I don't have you write down in a book. But anything we prove in class, like I said, I can't think of anything. Maybe we might do something, I don't know. But if I say it in class, we can use it, and you accept it, obviously, it's true. You can use as proof. Here we go. So postulates, theorems relating to points, lines, and planes. Most of this stuff I've already talked about, but we don't have it in our book of truth, so we got to put it in our book of truth. All right, here we go. We accepted all these without proof, right? Because they were just duh, they made sense. The ruler postulate, right? Any 2 points, you assign 0 and 1, and that's where we get all our numbers from. Same thing with the protractor postulate. And then the segment addition postulate, the angle addition postulate. You break a segment into multiple points. You add up all the distances of those points, right? The distance of those individual segments, they equal the big one. Same thing with the angle addition postulate. You add up all the individual angles that make up a bigger one, you get to the bigger one. Right? Those just were common sense ones. Today, any theorem I give you, we got to prove. Any other postulate will be an obvious one like those. So, more postulates, yay. That cat's happy. Postulate 5, write this down. Now, postulate 5 doesn't have a name. Well, I'm saying like the angle addition postulate was the name of postulate 4. But postulate 5 doesn't have a fancy name. It's just called postulate 5. So if you use this as proof for a theorem, which we will, you got to say by postulate 5. Who's going to remember postulate 5? This isn't Latin class where you got to memorize this stuff. You put it in your book of truth. You're like, oh wait, what's that one that says this? Oh, let's call postulate 5. That way you don't have to memorize. There's hundreds of these things that we will do this year. You're not going to memorize these things. All right, here's what, unfortunately, you got to write this down. There's multiple statements here. Write this down. A line has at least 2 points. Does that mean a line has 2 points? It means a line has at least 2 points. Most lines have it, or I should say all lines have infinite points. This is where we get that statement, 2 points define a line. Postulate 5. A plane contains at least 3 points. That's where we get the statement, 3 points define a plane. I can't say what I want to say because Karis hasn't taken her quiz. Now, here's the kicker. If I have 3 collinear points, that means you can draw a line through the 3 points. How many planes contain that line? How many flat surfaces can I put on that line? Okay, so here's my plane. It's better done in 3 dimensions than 2. Here's my line, hold this. So if this line is on the plane, it looks like this, drop it. Okay, the line is on the plane, right? So now you hold the plane, I'll hold it. Now move that around the line. There's a plane, I move it. There's another plane, keep moving it. There's a plane. How many planes are, an infinite. So if the points are collinear, doesn't work. We need them to be non-collinear. We need one of these points to not be on the line. So if one of those points is not on the line, now you have your 3 points, 1, 2, 3, that the plane can sit on top of like a stool. Okay? All right. And the last statement is space has at least 4 points. Space has way more than 4, but space has at least 4 points. And they can't all be on the same plane. So those are all the statements that we get from postulate 5. All right, you got it written down? I said today's going to be a lot of writing. So in summary, a line has at least how many points? A plane has at least how many points? All right, you can see where I'm going with that. Okay, so this is what postulate 5 says. You're like, well, couldn't I just copy that down and instead of that junk right there? No, I need you to write the words. Okay, we good? That's postulate 5. I just proved why. Postulate 6. All right, through any 2 points, there's exactly 1 line. Not 0, not 2, not 5, 1 line. I've shown that to you before. How come Oh, by the way, that's all. This one's a nice one. That's all you write. This is postulate 6. There are any 2 points. There's exactly one line. How come you can't have more? Remember, we don't prove postulates. We just accept that as true. How come you can't draw another line to those 2 points? Another unique line, I should say. Well, let's start a line, right? So I'm starting right here. I'm going to go to that point. How do I get to this point now? It turns into a curve to get to that other point. Remember, a line is defined as points that go in opposite directions. I'm not going in opposite direction now. I'm almost going in the same direction. That's why you're through any 2 points, there's only one and exactly one line. Good. This is a friendly one. Right? Why? I just showed you. I don't technically have to prove a postulate, but I kind of just did. Postulate 7. Remember, we're just doing some cleanup here. We've said these things before, but we didn't give them names. Postulate 7 says this. Through any 3 points, there's at least one plane. But through any 3 non-collinear points, there's exactly one plane. That's kind of the demonstration I just gave you. If the 3 points are collinear, yeah, there's one plane that goes through them. Any 3 points, there's a plane that goes through them. It's only when the 3 points are non-collinear that you get exactly one plane. You got a line, you can put an infinite amount of planes through it. But if you have 3 collinear points, therefore, they don't make a line, you can fit exactly one plane. This is postulate 7. We've made this statement before, but now we have a name to it. Who's going to remember this is postulate 7? None of you, myself included. This is why you have a book of truth. So if they ask you, well, how do you justify the fact that 3 points that are non-collinear make a plane? You say, well, that's postulate 7. You're going to be doing some flipping through your book when we have 100 of these. Luckily for you, by the time we get to, I don't know, chapter 3, we probably don't ever use this one again. Yes?
We have numbers that tell us how we do numbers in a certain set of numbers.
You don't hurt yourself there.
I'm overthinking this way too much.
Don't hurt yourself, Sal.
My head's starting to hurt.
All right. If you have 3 points, any 3 points, how many planes do you have? If you just have 3 points, you have at least one, right? But if you have 3 non-collinear points, remember that you can't draw a line through them, then that's the one where you have only one plane. If the 3 points are on a line, right? Sorry, you can flip a plane around this sucker. But if you have 3 non-collinear points, only one plane. That's postulate 7. We good? Moving on. Oh, when's it going to stop? It's not going to stop until May.
My birthday.
Every single section will have multiple. Typically, it's theorems, not postulates. All right, postulate 8 says the following. You see this? I said, when we draw this shape, what am I trying to show you? I'm trying to show you a plane, except when we get to chapter, was it 4 or 5? We get to parallelograms. And then you got to say, wait, is that a plane or a parallelogram, right? We'll wait for chapter 4 or 5. Okay, so if you have a plane, and I got one point on the plane, and another point on the plane, what would happen if I played connect the dots? I would get either a segment or a line or a ray, right? Where is that line or segment or the ray? Physically, where is it? That's what postulate 8 says. It says this. If you have 2 points that are on the plane, if you play connect the dots, it's not a curve, right? It's a line or a line segment or a ray, right? That particular shape is also on the plane. Question. Now this is technically a new one. I haven't talked about this at all. Once again, I'm not proving this to you, but it's really obvious, right? We will prove 2 today. You haven't even seen one yet. And we formally don't learn this until, I believe, chapter 2. how to do a proof. Then you're allowed to say you hate proofs. If 2 points are on a plane, it says a line, but just remember you could also draw a segment or a ray that connects the points is also on the plane. You overwhelmed yet? You should be. It's a lot. We're already to number 8. Oh yeah.
We're living in numbers.
You okay? All right. What would happen if I had not one plane, but 2? We've talked about this one before. If I have 2 planes, give me everything that could happen if I had 2 planes. The planes could be, as the picture depicts, they could be, say it, they could be, say it,
Parallel.
they could be parallel, right? Meaning they have no points in common. But they also could overlap or intersect. Now, what shape do they make when they intersect? And I don't mean this plus, right? Where they intersect, what shape does, we've talked about this. It makes a line. Can you see that? Like where they touch each other, right? It makes a line. Doesn't make a plus. Like, yeah, it does. I literally see the plus. These are the 2 planes, right? Not where they touch, but the 2 planes themselves. You'll never hear that question. But where they touch, it makes a line. So that is going to be Postulate 9. And there's an attempt at doing it in 3 dimensions, in 2 dimensions, if that makes sense. We're drawing in 2 dimensions. We're trying to let this represent 3 dimensions. So where the 2 planes intersect, it makes a line. This is Postulate 9, and it's real nice and short. If 2 planes intersect, then their intersection is a line. It's certainly not a segment because it goes on forever. It's certainly not a ray because it goes in opposite directions forever. It makes a line. 2 planes intersect, it makes a line. Like, I still see the plus. Well, the shape of the 2 planes, certainly, at least in this depiction, looks like a plus. But remember, planes go on forever, so it doesn't really make a plus. Okay, if such a thing exists, I'll go with that. Okay, there's Postulate 9. We've done 5 so far. And it doesn't stop. It continues. I believe that this is the one section that has the most theorems and postulates. I believe. Okay, recall this, that postulates we take as, we just accept them to being true without proof, although I technically did try to justify a few of those. Theorems are the ones that we must prove. We don't have that option. I have to prove every theorem. Now, in honors class, I will literally prove everything. In fact, that's all we do are proofs, right? We do fewer calculations and we spend our time on proofs. In a regular class, I flip-flop that. We're going to prove most things. There'll be a few things I say, no, I'm not going to prove this one. If you want me to prove it, I can, right? Because I did say I have to be able to prove things to you. But there'll be at times, and it's not that often. It's not like you get, half of the course, right? But there'll be times where I don't prove a theorem. All right, theorems we got to prove to be true. Okay, so to prove a theorem, we can use 3 things. We can use, it doesn't say that. It should say definitions, other postulates, and other theorems that have already been proven true. So as soon as we tell a postulate, you can use that. As soon as we prove a theorem, you can use it to prove other theorems. Here's your first one. So write this down. This is theorem 1.1. So it's chapter 1, the first one. Now, universally, generally those postulates I just gave you in most books, they're literally called postulate 1, 2, 3, 4, 5, 6, 7, 8. Theorems, okay, they can have any name they want. What's in chapter 1 of one book might be in chapter 2 of another book. Especially once we get in the higher chapters. All right, here's what it says. It says if 2 lines intersect, they only intersect at one point. Now, I've done a lot of work on this, and you can probably already accept that as true without proof, but I will prove it for you. If 2 lines intersect, they intersect at exactly one point, only one point, not at least or as many as, but only 1 point. So apparently I got to prove this to you. So let me see if I can prove it to you. All right. So it says there's an if and a then. You see the if and you see the then? So the if is the trick I'm about to perform. The then is how do you prove that the trick works type thing. So the if is 2 lines must intersect. So there's your if. Now I got to prove that there's no other way that they could intersect. Like there's not a second point where they intersect. Anybody want to try it? You're like, I don't even know what you're asking me.
I have a crazy idea. But if your line has thickness.
Lines have no thickness.
No. Well, that was my if.
And I get where you're going with that, right? Okay, let me try it for you. So this is not a formal proof. Like I will show you how to do a formal proof. This is informally done. All right, so here's your proof of it. So I got an if and a then. So the if is your starting point, how you start things. We also call it the given. I'm going to give you that 2 lines intersect, right? So if 2 lines intersect, right? Well, if 2 lines intersect, well, that means they must have 1 point, at least 1 point common, right? If they intersect. Otherwise, they wouldn't touch at all. So if they intersect, well, then there must be a point there. So this is my given, right? The 2 lines, a blue one and a red one, they intersect, and I just named it point A. I need to prove the then part. I need to prove that that's the only place where they intersect. Okay. Anybody want to try it? If they intersect, then guess a second point, guess what? Well, where do they intersect? If they intersected the second point, well, then they must have another point in common. Okay, so let's create that point. Well, there's B. So if they intersect more than 1 place, that means there must be another point somewhere along this red line. Well, how do you get the blue line now to go through here? You gotta make it a curve. I'll do it nice and neat now. Why is that bad? It's not a line anymore, right? You know, this contradicts the definition of a line. The definition of a line is, it extends for an infinite series of points in opposite directions. I'm not going in the opposite direction any longer, right? The opposite direction would go like this, and I just curved it around. It also would contradict Postulate 6. Karis, read me Postulate 6. Through any 2 points, how many lines are there? I got 2 points. How many lines go now through those 2 points? As I drew it. That contradicts what you accepted as being true. Contradicts, then it can't be true. Mike is 10 years old. Wait a minute. This birth certificate says that he's 15. That contradicts what you just said, so therefore it's not true. You see how that works? This is how you do proofs. Now, this is called an informal proof. A formal proof means it's in a nice formatting. We will have a format to it. We will do that later. Okay. Next, think about this. I got a point, right? And I got a line. Is the line on that point as I drew it? No. So you got a point that's not on a line, right? How many planes contain this line? It was the demonstration I did before. How many planes contain this line? So how many planes can I put on that one line? Well, there's 1. There's 2. These are different planes, right? They're not the same. 1, 2, 3, 4. So how many planes contain that line? Okay. How many planes contain the point and the line?
1.
How do you know?
That's 1 and the line. Move this up.
Do you agree with him? All right. This is Theorem 1, 2. And by the way, he just proved it. Right? Theorem 1, 2 says that if you have a point and a line and they're not collinear, then there's only 1 plane. Through a line and a point not on the line, they love that saying. Through a line and a point not on the line, that just means they're not collinear. There's only 1 plane. There's exactly 1 plane that touch both of them. Hey, there's an infinite number of planes that touch the point. Hey, there's an infinite number of planes that touch the line. But there's only 1 plane that touches both of them. Now Matt said, well, think about it. You put the plane right here, I'm touching the line, but I'm not touching the point. I put it right here, I'm touching the line, I'm not touching the point. That's the only plane that would touch both of them. This plane right here, in fact, the board, is the only plane that would touch both of them. Now that's a good visual proof. I can prove it using the postulates. Right? So think about this. Wait, sorry. Let me go back. We good? Okay. Moving on. Think about this. We've got a line. How many planes contain a line? Infinite. Right? Theorem 1.3 says this. If you have two lines and they intersect, how many planes touch those two lines? If you have two lines that intersect, how many planes touch those two lines? Well, it says exactly one. This one might be one you might not accept without proof. And I will prove this one to you. I'm going to use Matt's proof is for 1.2. But I got to prove this one. Because you might be thinking, well, maybe there's a way of drawing it so that they don't touch one plane. This is a hard proof. This would not be a proof that I would expect any of you could do even at the end of the course. We good? We got it written down? I think this is the last one, by the way. All right. So here's the proof. So the if was, or the given was, two lines intersect. So there's two lines that intersect, right? Where they intersect, I don't know, right there. What I got to prove is that there's only one plane that contains those two lines. All right, let's see if I can do this. I better. By Theorem 1.1, what does Theorem 1.1 state?
Two intersecting lines.
So the only point they can have in common is A. So by Theorem 1.1, there is no other point that they have in common, the two lines. We okay? Like, where's he going with this? All right. Well, by Postulate 6, there must be a point B. What's Postulate 6 say?
So through any 2 points, there is exactly one line.
So blue is a line, right? It has to have at least 2 points, right? Well, I'm just going to say point B is that second point. There's an infinite number of points, but just for instance, why do I know that B is not on the red one? It says if they intersect, there's only one point they have in common. And we already said that was A. Well, by that same Postulate 6, there must be another point on the red line. I'm going to call that C. Where am I going to try to prove that only one plane contains those three? Look at these 3 points. Are they collinear or are they non-collinear? You said non-collinear. Are these 3 points on the same line or are they on different lines? Right? By construction, right? I've got that one. By construction, I made points A, B, and C. I mean, I constructed that. And I made them non-collinear. What does Postulate 7 say? What does it say?
Postulate 7 says, through any 3 points, there's at least one.
Keep reading.
And though any 3 non-collinear things,
And through any 3 non-collinear points, that's why this is true. I made this construction, and I made it through 3 non-collinear points. And there's 3 non-collinear points. By Postulate 7, there's only one plane. There, I proved it to you. You want to know why people hate proofs? Right there. The only difference between this and a formal proof, it's prettier. It visually looks prettier. This is the actual proof of this, by the way. We will just do this in a more formal way. And this is hard. I'll just say this is a hard proof. I would not expect any of you to have been able to come up with this by yourself. Trust me when I say I will take care of you this year if you try. If you try, I'm going to give you proofs that you can do. This ain't a proof that you can do by yourself. This is the typical proof that I will do in class to prove things to you, and then you will say, okay, I now accept 1-3, we're good to go. The only proofs that I will give you are proofs that you are capable of doing. And by that I mean I'm going to keep the bar high. I'm going to give you hard proofs, but proofs that you can do if you try. Problem with geometry is you will give up very quickly, right? I don't know how to do this, I quit. Some of these proofs you got to spend an hour thinking about, okay, I'm thinking about it, but I can't do it right now. I'm going to come back to it in an hour. And then maybe in an hour, your brain kind of figures it out all by itself. That's it. Nothing left. All right. What the heck did we just do? The whole class. Literally, what did we just do?
Postulate theorem.
All we did was write stuff down. We didn't do any work. So what in the world could the homework look like?
Writing things down.
If you run into a problem, you email me over the weekend. I can't guarantee you I'm going to answer back within an hour or two, especially if I play golf on, which I will on Saturday. But I will send you some help. Right? Give it a shot. We don't have a student advisement today after this class. So give it a shot. Try 2 through 12. All right. Any questions? That's all. Paris wins your quiz. Oh my God, was that good or what? Man.
Really getting this teacher thing down.
I know, it only took me 11 years. All right, have a great weekend. Do something fun, and I got to hit